Thanks everyone for joining my talk today. We'll be taking a glance at interpreted language bytecode trickery. As Kieran said, my name is Chris Lyne. I'm on Tenable's zero-day research team. The team's goal is to discover unknown vulnerabilities in third-party products. We'll also coordinate disclosure with the product vendor. And also we do quite a bit of sharing our research with the community. So some quick background on the talk. It started off with two research projects, one of which I looked at druva insync, which is an endpoint backup solution. So that one's written in Python. And there was another project, Nagios XI, which is an enterprise server and network monitoring software. That one's written in PHP. So the main goal when I first started these projects was to get a hold of their source code and read it, figure out how the product works, see if I can find vulnerabilities. But in both cases, I was presented with bytecode protection. So I wasn't able to just read the source code like I had hoped. So some topics for today that we'll go over. We'll talk a little bit about interpreted languages. We'll talk about what bytecode is. We'll talk about the protections I encountered. And also we'll go through how I bypass them. So real quick, let's talk about compiled versus interpreted languages. So on the compiled side of things, you're probably familiar with C or C++ or Go. Those are all compiled languages. But basically, you have your source code program. The programmer has to explicitly compile that source code into an executable format, which is machine code that targets the operating system and the processor. So for this talk, we'll be focusing on interpreted languages, like such as Python or PHP or Ruby. It's different than compiled language because the programmer doesn't have to compile it explicitly. There is an interpreter that does that job, and the interpreter will convert the source code into bytecode, which is similar to machine code, except that it targets a virtual machine environment. So the Python virtual machine or PHP virtual machine. So first we'll take a look at Python opcode remapping, and that was in the druva insync product. Then we'll take a look at the protection, code objects, and fixing the opcodes. So in druva, one of the first things I did was analyze the program behavior. And at the top here, you can see procmon output. So that shows some events that took place when the insync program launched. And as you could see, a Python 2.7 DLL was opened, and also a library.zip archive was opened, which is down here. So this type of behavior is indicative of a Python application that's built with Py to exe. Basically, what it does is it allows the developer to write Python code, but then they can ship their application as a Windows executable. So essentially, it ships it with Python and all of the Python libraries that are required, which is what you see in here. If you notice, all of the files in here, for the most part, end with .pyc. So again, those are the modules, the Python modules. So you might be asking, well, what's a PYC file? And the answer is that it's a byte compiled Python file. So if you were to load up a PYC file in your text editor, you're not going to be able to read Python source code like you would with a .py. The idea of compiling a Python file like that is to help speed up the load time. And this especially is true with modules, because as you saw, there are a lot of modules. So if they're already compiled, when they're imported, it really speeds things up. However, if you wanted to read the source code of those compiled files, you would need to use a decompiler, such as uncompile6. And that's what I've showed you here in this screenshot. I used uncompile6 to decompile the Python struct module. And as you can see, it works pretty well. Basically, that module is just a few imports. Now, the protection I encountered it when I tried to decompile the struct module that was shipped with druva insync. Now, when I tried to decompile it, I got this interesting error, unknown magic number 62216. So clearly there was something in the PYC file that uncompile6 didn't like. So my next step was to figure out, well, what's the structure of this PYC file? What's going wrong here? So when I was trying to learn about the PYC format, I started off with a hello world application. It's just one print statement. I used the PyCompile module to create a PYC from that source code. And at the bottom here, you see a hex dump of that PYC file. So the first 4 bytes of a PYC file are what's called the magic string. The next 4 bytes are the timestamp of when the file was created. And then following all of this is a code object. We'll talk more about the magic string and code object as we go. So that magic string I just mentioned to you contains a magic number. And if you remember, the error before said unknown magic number 62216. If you look in here, this is a list of documented magic numbers. So like 62211 corresponds with 2.7A0, and actually many of these correspond with that Python version. So with each magic number, you can see that something's introduced, right? So we introduce setup with build set, we introduce map add, we introduce set add. These are all Python instructions, or bytecode instructions. Now, all of these bytecode instructions have a corresponding opcode. So for instance, the highlighted line here, and this is defined in the opcode module, the highlighted line here shows that the call function instruction maps up to the 131 opcode, and so forth. Make function maps up to 132, build slice maps up to 133. Now, there are quite a few of them. Now, if you were to use the opcode module, so we'll import opcode and dump out the opcode map, you can verify that number we just saw. Call function maps up to opcode 131. And so take note of that one. Also take note of dupe top maps up to 428. So if we were to do the same thing with the druva installation, we import the opcode module that was given with the druva installation. Check out the op map. Notice that call function has a totally different op number there. And so does dupe top. I'll go back so you can see that. The 131 and 4, 111, 64. So now we'll look at code objects a little bit more in depth, as that's where the instructions and opcodes are contained. So that code object that's in the PYC file, if we were to read from a PYC file, load up the code object that starts at index 8, use the Marshall module to load those code bytes, you can see that there is a code object in there. And if we were to execute it, we would get that expected output, hello world, right? So in that code object, there is a field called cocode, which contains the raw bytecode. So this string you see right here, this is raw bytecode. It contains, at the beginning here, this D it's an opcode. And then each opcode has operands following it. So the arguments to the instruction. Now, since we're trying to decompile a compiled Python file, I should want to tell you about disassembly real quick, because that's an intermediate step in between decompilation. So those opcodes can be disassembled. You take a code object, use the dis module, and you can disassemble the bytecode. So as you can see for that hello world, it ends up being quite a few instructions compared to the Python source file. You have a load const, which loads the hello world constant, which is defined in the constants tuple. That constant is printed, a new line is printed, and then the script returns none. Now, in the real world, obviously, we're not going to see hello world applications. We'll see more object-oriented like applications. They're much more complex. And still, this is a fairly simple example. But if we take, for instance, the hello class, it has a blank constructor, doesn't do anything. And then there's a method called say hello that just says, oh, hey. If we were to disassemble that code object, I want you to notice here at instruction at offset 9, we're loading a constant, which is a code object. So if we were to look into that constants tuple, at index 1, you would see that there is indeed a code object. Now we can disassemble that code object too. And in fact, it contains some instructions to load even more code objects. So as you can see, a basic class can start to get pretty complex. You have nested code objects. Now we'll start getting into how I went about fixing these code objects in order to decompile this stuff. So my strategy was to, you read a PYC file and then take a look at all the opcodes in the bytecode. So we know that we have the mapping for the druva opcodes and we have the mapping for a normal Python 2.7. If we see a druva opcode of 111, we know that it's a call function instruction. Now we can replace that opcode with 131 and so on. If we see a 64, we know it's a dupe top, then we'll replace it with a 4. So ultimately, because of the complex nature of code objects and how they can be nested, the algorithm had to be recursive. So just bear with me. We're going to go through this diagram real quick. So obviously, we're reading a PYC file. It has a magic string, a timestamp, and that code object we're interested in. So we read the code object. And then there's a main function that I implemented for fixing code objects. So when the code object comes in, that raw bytecode in the code field is remapped. So like we saw before. And then we also saw that the constants tuple can contain nested bytecode. So if there are more code objects in the constants tuple, we'll go ahead and loop through those, pull out a code object, and then call this routine again. So that's where the recursion comes in. And the whole idea is to produce a new code object with remapped opcodes in code, and then remapped opcodes inside the nested code objects in this constants tuple. And ultimately, in order to make decompilation work with a standardized tool, I set the magic number there to 62211, which was Python 2.7 A0. I also set a timestamp of today, right? And then that new code object is stuffed in there. So after I did that after I ran that routine on all of the PYCs that were delivered with druva insync, I was able to decompile them. Unfortunately, I can't show you all their source code because it's their intellectual property. Yeah, so that's Python opcode remapping. Next, when I was looking at Nagios XI, I ran into PHP source guardian. And this is a proprietary protection mechanism. So when I was looking through their code base, they had all sorts of PHP files, some of which I could read the source code, and then there were others that looked like this. And I don't know about you, but when I look at this, I can't read any of this. There's no programming logic in here. Basically, what this is an encoded file. So if you were to run the source guardian encoder on a PHP source file, you would end up with something like this. Notice at the top here that it checks to see if the sgload function exists. And if so, we make our way down, then the sgload function is called. And what this code does is it allows source guardian protected files to decode themselves and execute themselves. Now, if we zoom in on that SG load call, there's a big string of stuff. And this is the programmer's logic that we're interested in. So I'll take a quote off of the Source Guardian website. They describe their product. They say, our PHP encoder protects your PHP code by compiling the PHP source code into a binary bytecode format, which is then supplemented with an encryption layer. So they compile the PHP code and then encrypt it. Now, this SG load function has to first decrypt, then execute the bytecode. So this argument here, this is the encrypted bytecode. So that's what we're after. So we'll take a look at a few quick internals concepts. So PHP bytecode it's similar to Python in that, it's a bytecode format that the VM understands. However, I'm not aware of a concept of a PYC file in the PHP world. However, there are PHP extensions that will precompile scripts. And here's a quote: the opcache extension improves PHP performance by storing precompiled script bytecode in shared memory, thereby removing the need for PHP to load and parse scripts on each request. So same idea, scripts are precompiled into bytecode for speed purposes, right? Now, in general, when a PHP script is executed, it does get compiled into bytecode, which is then executed by the Zen VM runtime. So PHP and the Zen engine also provide different hooks for extensions. And these hooks allow extension developers to control the PHP runtime in ways that are not available from PHP userland. So some hooks that we'll talk about coming up here are Zen compile file. So think about when PHP source code is transformed into bytecode. That bytecode is then executed. So we could hook send execute. And also each instruction, just like in Python, has its own specific opcode. And those opcode handlers, the functions that know what to do with those instructions, those can be overwritten as well. And something I'd like to point out here as well is that hooking is extremely useful for debuggers. If you think about some debugging you've ever done, you probably set a breakpoint on a function name. So that's the same concept. You would hook that function name. Now, in order to pull this bytecode out that I was interested in, I used an extension called the Vulkan Logic Dumper. And the Vulkan Logic Dumper allowed me to dump the instructions of a PHP script. It did it at compile time. So when this source code is compiled into bytecode, that's at the point where it's dumping it. So as you can see, there's an echo that goes hello world and a return 1. Now, when I tried, VLD, like I said, hooks Zen compile file. This is a snippet from VLD that shows how that works. So first the script is compiled, and then it compiles it into an op array. And that op array contains the bytecode, and then VLD dumps the op array. So that's that output you saw here. This is VLD dump op array. Now, if you were to run VLD as is, and it hooks at compilation time, if you were to run it against a source guardian protected file, you wouldn't get the output that we're interested in. We're interested in what the Nagios XI developer implemented. However, what you would see is that source guardian wrapper that I was talking about before. This is all the bytecode that would run in order to decode and execute the protected bytecode. As you can see at the top here, like we saw in the source code, it looks for that SG load function. If it exists, then eventually it would get called. However, the the output is pretty lengthy, so it's not shown here. Okay, so just let's take a step back real quick. So if we're visualizing the hook that we want, we know we don't want it at compile time. But basically when a source guardian protected file is launched by PHP, the interpreter launches, all of the code is in there to decode the compiled encrypted bytecode. At compile time, which we just saw, it would be compiled into bytecode, which is a Zend op array. This includes that call to sgload. And then after compiling the wrapper, that code would get executed, which in turn would execute sgload. So sgload would fire, it would decrypt the encrypted bytecode, and then call Zend execute to execute that protected bytecode. And that's the bytecode we're interested in. So the second invocation of Zend execute is what we want to hook. So my next step was to modify VLD. And I did this just like we talked about. I hooked the second invocation of Zend execute. So here's my VLD hook. So I wanted to see when execute ran. So I printed out execute, and then the op array would be dumped. And then finally the bytecode would be actually executed. So with the hello world, we can see that the hook was hit, execute was printed, and clearly the instructions were executed successfully. However, you don't see any instructions like we did earlier. The question was why? Why am I not seeing any instructions? And at this point, I decided I needed to debug the PHP process when I launched this encoded file. So I set a breakpoint at Zend execute. As you can see, it was hit twice. We're interested in the second one. So at the second breakpoint here, I printed out the op array. And as you can see, there are 3 instructions. And line start is 0 and line end is 0. And that was weird because if you looked at all of the individual instructions in the op array, and actually the instructions are Zend ops, each of these had a line number of 0, which was kind of strange. But if you were to look at the structure, you can see it has a handler, it has operands, line numbers. Now, I dug into the VLD source code to try and figure out why the instructions weren't being dumped. And I ran into a function that dumps individual instructions. And I found this interesting if block. If op line number equals 0, which they all do, we return, we don't dump anything. So I went ahead and commented that out. And I got some new output. So that was pretty exciting. So at the top here is my modified VLD against an encoded file, encoded hello world. And at the bottom here is VLD run against the hello world prior to being encoded. So this is not an encoded file. This is what we're expecting to get. However, the output I got was interesting because the number of ops were increased. You'll notice there are 3 up top and 2 at the bottom, and that there is an additional instruction prepended. There's a jump at the beginning. But if you trace the jump to instruction at offset 2, then it would simply return and the echo would not get executed. So the control flow is a little off there. Now, I wasn't sure why this was happening. So naturally I started off, creating more samples. And this was my next sample. I generate a random number, which will end up being either 0 or 1, depending on that random number. I'll echo 1 or 0. So I reran this test. Again, the encoded version's at the top, the unencoded version's at the bottom. And notice that, again, there are more instructions. There's an additional jump. If we follow the jump to 4, what happens here is a function call to ran takes place, but only 1 is passed as an argument. So if we jump straight to 4, then 0 doesn't get added as an argument. So that doesn't match up with the source code. Additionally, if you were to look at the output down here, there's a jump Z, but there is no jump Z and Z. So it looks like that instruction got changed. So I went back to the debugger for the hello world. If you remember, there were 3 instructions: a jump, an echo, and a return. Now, something that stood out to me was the jump handler address didn't point to a symbol like the other 2. As you can see with the echo instruction, the handler has a symbol associated with it, Zend echo spec const handler, and the return has a symbol associated with it. So that was kind of strange. I looked into this address for the jump handler to see where it was in the loaded libraries, and sure enough, it actually pointed into the source guardian extension. So this weird file name is the source guardian loader extension. I set a breakpoint on that address, and sure enough, once that function fired, I was inside of the source guardian extension there. Now, when I disassembled that source guardian jump handler function, there was a specific instruction that stood out to me, and that was the call. So inside the source guardian jump handler, it's calling another function at a pointer. It's a function pointer. When I stepped into that function, sure enough, the Zend jump handler was called. So basically, a bunch of stuff happens when a jump is encountered, and then the actual Zend jump handler is called. If you were to look at the operands of the jump instruction before entering the source guardian jump handler, and then compare it to inside of that source guardian jump handler right before the Zend jump handler got called, you would notice that operand 1 actually changed. And since it's a jump, the operand 1 is a jump address. So the address of the jump changed, which means that the jump would then jump to a different instruction. Now, just to kind of recap on that, inside the source guardian jump handler, this is the logic. So first, that jump operation is referenced. The operands are deobfuscated. And then the default implementation of the Zend jump handler is executed. After that, the operands were re-obfuscated to their original state. Okay, so now we'll start getting into my solution. So I started off with this jump instruction. How can I fix just one jump? So my solution was to modify the source guardian jump handler function, but create my own new function. So when a jump was encountered, my function would run. So I copied some of their code to allow for the operands to deobfuscate. However, I did not allow the Zend jump handler to run. Instead, I set the current ZendOps handler, that jump handler, to be the actual Zend jump handler. And then I didn't allow the operands to restore to their obfuscated state. So that's just for one operation, but we have to fix the entire op array. So if you remember back before, when we would dump an op array, it would just show the obfuscated values. And then once the op array was executed by Zend execute, the source guardian handlers would run for a Zend op. The operands would be deobfuscated, then the real Zend handler would run, and the operands were obfuscated again. Now with my solution, I added a step at the beginning to fix that op array. So using the same logic from the source guardian handlers, I would allow the Zend operations to deobfuscate as intended. And then I would set the handler for that operation to actually point to the Zend handler. So then when I dump the op array, you would see those corrected operands. And when the actual op array was executed, the Zend ops would execute correctly because the operands were deobfuscated and the handler was pointing to the Zend handler. And okay, so I told you about the jump handler, but there were several different source guardian opcode handlers for different types of instructions. So I've grouped them into 5 different handlers here. So source guardian had 5 different handlers. Depending on the opcode value, it would determine which handler was called. So I ended up having to create 5 of my own. As you can see off to the left here, I would loop through the op array, look at every instruction, and depending on the opcode value, I would call a specific function to fix it. As you can see at the top here, if it's 42 or 100, I call the fix jump. This function handles these opcodes and so on. So we've seen how to fix an op array. Now, like in the Python world, classes create a different layer of complexity. Here's another example. We have a class 1 and a class 2, each of which has either a func1 or func2 that echoes 1 or 2. Each class also has a function that is not used. So it's not used 1 or not used 2, and they return 1 or 2. Now, I define these classes, and also I have like kind of a main function here. Generate a random number, 1 or 2, depending on the value. Either class 1 or class 2 is instantiated, and either func1 or func2 will be called. Now, when I ran my modified VLD against this, here's the main that we saw, right? We generate a random number, depending on the value, either class 1 or class 2 is instantiated, func1 or func2 is called. And for this particular case, the random value was 1. So as you can see, func1 was dumped. However, the not used 1 function was not dumped, and class 2 entirely was not dumped. So I only got the output for the instructions that were executed, the main and class 1's func1. So in order to dump it all, I had to tap into the class table and the function table. So like we saw before, I have that fix op array routine, which would fix the main. And then I would have to tap into the class table, which contains class 1, class 2, and all their functions. And in this case, we didn't really have any functions, but outside of the classes. But all of these would need to be processed as op arrays. And then at that point, we would dump the op array. And so then I was able to view the instructions for not used 1, and additionally, class 2 entirely. So thank you all for joining. Just to recap, we talked about remapping Python opcodes in a static PYC file. And we also fixed PHP bytecode at runtime. Hopefully this talk helps you down the road when you encounter a similar protection mechanism. If you're interested in diving in a little bit deeper, I have written a couple blogs on the topic, and all of my source code is available online. And at this point, I will open it up for questions.
Thank you, Chris. Very interesting. Normally, I can have no opinion on most talks that are given, but this was like a different language to me. So very, very interesting, very technical. So thanks for that. Just going to check the questions tab there and swap card. Just give me a second. So there have been no questions yet. So I'll just give folks another maybe 10 or 20 seconds.
Sure.
And if there's no questions, then we'll give you back maybe 8 minutes. Okay, there's no questions coming in, Chris. So thanks again for your time today. The feedback was very good on the chat, very informative from lots of folks. So thanks again for your time, Chris, and enjoy the rest of your day.
Awesome. Thank you for having me.